I request Dr. Gopu R. Poti, Professor of University of Rhode Island, USA, to give the keynote address on the effects of climatic change on underwater acoustics.
Gopu R. Poti is an Associate Research Professor in Ocean Engineering at the University of Rhode Island, USA. His areas of research include underwater acoustics, acoustical oceanography, marine bioacoustics, acoustical signal processing, inverse methods, and application of Bayesian and machine learning techniques in acoustics. He has been actively involved in various research projects investigating the impact of offshore wind farms on environment with specific focus on acoustic noise and particle velocity. He is a fellow of Acoustical Society of America, member of IEEE Oceanic Engineering Society, and serves as an associate editor of IEEE Journal of Ocean Engineering.
Thank you, everybody. Thanks for invitation to this meeting. I have been participating in this meeting for a while now, and it has always been a pleasure to come here. Many of you know that I was a faculty at Ship Technology next door, and I have friends and colleagues who are still here. So it's nice to come back and touch base with them and interact. Before I start, I would also like to say a few words about Dr. Srinivasan and Dr. Sridhar. I know both of them. I knew both of them very well, and I had the pleasure and privilege to have serious discussions with them on numerous occasions, and I'm sad that they are not here today. But I hope that their vision and the projects and the problems that they have started investigating will continue with the young crop of students. So with that, let me start talking about the topic here. In the inaugural function, a few of the speakers talked about the importance of climate change, and probably some of the most talked about issue in the world today. Most of the controversies and discussions are on the societal aspects of climate change. But I won't go into the societal aspects. My concern today will be purely on its effect on underwater acoustics. Now, it's well understood that ocean plays an important role in absorbing some of the impacts of climate change. Specifically, it absorbs about 93% of the excess heat in the atmosphere. It basically acts as a sponge, sucking up all the excess heat in the atmosphere. It has its own implications, but still it removes heat from the atmosphere. The other aspect is it removes around 30% of the excess carbon dioxide generated by human activities since the pre-industrial times. So that increases the acidity in the ocean, and that particular problem is called ocean acidification. That has its own amplification, which I will talk a little bit down the road. So as it becomes a repository of heat and carbon dioxide, the oceans has become warmer, more acidic, and undersaturated with respect to carbonate. It's also losing oxygen because the warming affects the solubility and vertical mixing. In the context of oceanography, these changes are accompanied by changes in stratification, and stratification has very significant role to play how sound propagates in the ocean. It also affects the nutrient availability, so that affects the distribution of marine organisms. Surface primary production, which affect the carbon export in the deep, and food supply at depth. So the food supply affects the food supply chain, and one of the things that we have been seeing over the years is the migration of marine mammals and fish from place to place, depending upon the availability of the food and the oceanographic conditions. That has some impact on acoustics also. So these changes, which are already happening, and it's anticipated that it will happen more often and more increasing amplitude. So these changes will alter the thermohaline conditions. The thermohaline meaning the temperature and salinity distribution in the ocean, and most of you know that sound speed is dependent on temperature and salinity. So if temperature and salinity distribution changes in the ocean, that will affect the sound speed structure in the ocean, and sound speed structure changes, then the propagation of sound will change. So I'll go through some of the anticipated changes, some of the changes which have already been measured and is already happening, and some of the changes which in itself may not be significant, but when combined with all other processes will magnify the effects. Everybody is concerned about sea level rise. Anybody who lives in the coastal region worries about it nowadays. Coastal flooding is happening increasingly. I live in a coastal town, so I know it firsthand. So that's one of the major significant signature effect of climate change. Some impact on acoustics, but not a serious problem. We'll mention that in passing. So I put together this slide just to highlight the breadth of issues that climate change poses to all of us, the engineers and scientists. So on the one hand, people worry about the causes. What are the causes of climate change? I'm not a climatologist. I cannot talk about the causes with any authority, so I won't go into that. And also that's a little bit political in nature, society, a lot of social issues. So that's not my field. On the other side, the things which we can measure, that we can perceive, are the effects of climate change. Some of the effects I already started mentioning. And of that, there are all kinds of effects, and of that, there are some effects to underwater acoustics. People have not been paying much attention so far, but slowly people are starting to pay attention, mainly because of naval interest. Most of you know that research in underwater acoustics is mostly driven by Navy. So if Navy is interested, things will happen. Of those effects, most of it is oceanography related. So oceanography drives acoustics for the most part. In shallow water, the bottom plays a part, but bottom doesn't change, it doesn't go anywhere. So most of the dynamic nature of changes in acoustics is driven by oceanography. Some of the changes are driven by climate change, which changes the distribution of noise sources in the ocean, and one of the terms which is collectively nowadays used is soundscape, ocean soundscape, which sort of represents or the distribution of noise sources in the ocean. That changes, and that will have an impact in the way people do business in underwater acoustics. We already mentioned about ocean acidification. There have been studies done to assess the impact of ocean acidification on underwater acoustic propagation. So I will briefly discuss that too. Now, one of the interesting peripheral issue is, so people suggest a lot of remedial measures to combat climate change, reduce the carbon emissions. So one of the things is used to use alternate sources of energy, renewable sources of energy, and one of the prominent one is wind energy, and there has been a lot of initiatives to have wind turbines, wind farms offshore. Europe is leading the way. There has been tons of wind turbines in the European waters. US is getting into that business. The interesting thing is that there is a positive aspect to that, but still we are not sure how that is going to affect the soundscape and how that is going to impact the marine life in the ocean, the fishes and marine mammals. So that's an interesting conundrum. So with that introduction, I'll just outline the topics that I'm going to talk about. So most of the impacts that I'm going to talk about vis-a-vis acoustics is related to shallow water. So I'm in shallow water acoustics. Most of my work is in shallow water. So that's what I know better. So I'll focus on shallow water, and that too in the eastern United States. The other, probably the biggest impact of climate change is being felt in the polar regions, and everybody talks about melting ice, and there are other issues related to stratification also there. So that's the second location that I'm going to focus on. So these are the two areas which I will focus on. As I mentioned earlier, I will slightly mention acidification and renewable energy towards the end, and then close up the talk. Before I start, I should thank the pioneers who started working on this, starting from Jim Lynch, who was my mentor. So these references are available. Most of it is open literature, so you can grab them if you are interested. So let's, before talking about the changes in acoustic propagation, the driver of that is the changes in oceanography. Let's briefly look at that. Ocean warming. Recently, the data collected in the eastern United States see that, based on that, we see that the Gulf of Maine and the southern New England, which is the area where most of my work is, that those areas are the among the most rapidly warming regions in the world ocean. The reason being the Gulf Stream, the behavior of the Gulf Stream, the erratic behavior of the Gulf Stream. Gulf Stream is, many of you, probably not many of you are aware, so it's a current which passes along the east coast of the United States. It's like you can imagine it as a river of warm water warmer than the neighboring seawater running along the eastern United States. I mean, typically it stays at the edge of the continental shelf. You know, the seafloor from the coastal region slopes very gently until it drops deeper at a transition point, which is called the shelf break. So typically the Gulf Stream hugs the shelf break. If that's the case, nothing is fine. But occasionally it meanders, it wanders into shelf region, carrying the warm water. Sometimes eddies spin off from the Gulf Stream, and then they propagate into the shallow water. So those kind of incidents bring warm water into the shallow regions of the continental shelf. So those eddies are called warm core rings because they are warm. So it has been investigated. So there have been a lot of studies on the behavior of the Gulf storm and its impact on regional weather. So the consensus among oceanographers and atmospheric scientists is that the significant cumulative warming could affect the intensity and severity of the storms striking the eastern seaboard and could alter critical habitat of commercial species. So the other impact is on the biological organisms which habitat the ocean. So they follow the oceanography. So fish and marine mammals who tend to live in warm waters, if the oceans are getting warmer close to the eastern United States, they will migrate to those regions, and that will have impact. So everything is a well-balanced system, and if something changes, then everything changes. So that's the Gulf Stream I have been talking about. So this is a kind of a nice river-like current which passes parallel to the east coast. And the shaded region there shows the meander over time on 2 years. So this color represents the extent of the meander, the bounding regions of the meanders in 1995, which is pretty narrow. In 2004, it basically wanders much farther into the. So this is the eastern U.S. coast, and you can see that in 2014, it basically wanders much eastward, bringing warm waters. So continuous measurement over the years have shown that the Gulf Stream meanders, these wanderings, have increased in amplitude and initiated much further west over the past 20 years, bringing Gulf Stream water closer to the continental shelf of the New England. So that's the data. Nobody can dispute that. So this is a satellite picture of sea surface temperature. You can clearly see the meandering pattern of the eddies spinning off from the Gulf Stream there. So this color, the red and orange, are warm waters, and you can see that this is the Gulf Stream going this way, and this is the spin-off from that Gulf Stream. And these are measurement locations which are permanent, which is continuously measuring the sea surface the temperature and salinity of the ocean. The measurements done somewhere here, these two locations here in the continental shelf are shown here on two years, January and February in 2 years, 29 and 14. So this is salinity and this is temperature. The red is salinity and the blue is temperature. And in January, the temperature as well as salinity is lower. It's winter, so temperature is very lower. And early spring, which is February 14, it's still end of summer. You can see that the temperature has increased by as large as 5 degrees, which you put into the sound speed equation will transform to 20 meters per second. So that's significant change. Not only that, it changes, and you can see that the bottom, the profile itself has changed. So this is constant, almost constant. Winter is always rough. There's a lot of storms, so the water gets mixed well, and you get a nice isovelocity layer. But you can see here, because of the intrusion, you get a bottom layer of warm water, which has significant impact on acoustic propagation, which we will see in a second. One of the reasons for this warming and cooling effect is the jet stream. Jet stream is the most heard term weather forecasters used in US. So it's basically the boundary between the cold Arctic air, Canadian air, and the warm southern US air. So the boundary is jet stream, and that goes up, meanders up and down. And recently, it's fluctuating a lot, and that is creating a lot of storms in the US. And it creates this cold pools and warm pools of air, and the atmosphere interacts with the ocean a lot, so that also has some impact on the warming of the oceans. I mentioned the other important area of action is the Arctic. And sea ice, thinning of sea ice is one of the important effects of climate change in the Arctic. The other important effect is the changes in the nature of stratification. You see, the thinning of the ice has something to do with that, and these changes in stratification is having profound effects on the acoustic propagation across the continental shelf and slope of the Arctic. So basically what happens is that there is a surface layer of cold water, and then below that there is a salty, colder layer, more salty, and below that there is a warm Atlantic water. So the water becomes stratified with a cold water pool in the middle, which is called the Arctic layer, Arctic halocline. Thermocline is the change in temperature with depth, drastic change in temperature with depth, and halocline is the drastic change in salinity with depth. Both temperature and salinity affect sound speed. Temperature affects the sound speed to a higher degree than salinity. So, for acoustics, what happens is that this layering structure leads to important propagation effects relating to long-range propagation. So we'll see that in the next few slides. We'll start with the probably the acoustically insignificant impact of climate change. It's significant in other aspects, but not acoustically. That's the sea level rise. So basically, the water depth rises, coastal areas get inundated. The playing field for acoustics becomes now shallow waters, coastal waters, and things like that. But in shallow water, I mentioned bottom plays an important role. The advantage of having flooded coastal region is that the coastal regions have been previously land and has been surveyed and cored and sample to much higher degree than ocean waters, so we have more data, so modeling is easy. So it's ironic that this problem of coastal flooding and shallower propagation, newer propagation areas is not as bad as the other effects for underwater acoustics. So that's why I just called it's an acoustic benefit within quotes, but it's not a benefit for other if you consider any other aspect except for acoustics. To explain some of the other effects, I have to explain a little bit of underwater acoustics. I'll be general. I know that not many of you are acousticians here. So this is a typical ray diagram in a shallow water environment. So this is the bottom in gray color, and this is the surface of the ocean. And let's assume that there is a source here sending energy in all directions. So So these lines are acoustic rays. It sort of indicates the direction in which acoustic waves are propagating. And when the rays or the waves hit the bottom or the surface, it's going to reflect, and some of the energy is going to refract into the bottom. And these two dark black lines are bounded by the quantity here called critical angle. So a source in a waveguide produces a sound field that propagates at angles confined to a critical angle 2 times theta c. So basically like a torchlight sending acoustic energy into the ocean, and the most of the sound is confined into this cone bounded by the critical angle on either side. So within this cone, constructive interference selects a discrete propagation angles. So so there are 2 ways in which you can think propagation, many ways, but 2 main ways in which you can think acoustic propagation in ocean. One is through this concept of rays, propagation rays. The other is normal modes. So these rays, when it travels, will constructively and destructively interfere, producing vertical interference patterns, standing waves, which are called normal modes, which are the propagating normal modes, which propagate along the range over long distances, will have a wave number associated with that, and the wave number in turn can be related to the critical angle. So it's the same propagation physics seen using 2 different modalities. So within this cone of plus or minus theta c, constructive interference select discrete propagation angles. The sound will propagate in range. Outside this cone, anything which falls outside this cone, in either direction, will interact with the bottom, and sound decays exponentially in the bottom, so it will eventually, it won't go far if you are outside the critical angle. So this is the math or physics associated with that. So on the x-axis you have the angle, grazing angle, and the critical angle is shown here. In this particular case, the critical angle is 33 degrees or something like that. The quantity that is plotted is the reflection coefficient, which is sort of a metric which will capture the energy which is reflected back into the waveguide or in the ocean. If you have a reflection coefficient which is close to 1, which is good, so most of the energy is coming back. If it it is 0, which means that nothing is coming back. So it's a ratio of the reflected energy to the incident energy. So as you can see that up to the so this is an ideal situation, no shear, no losses, nothing. So just pure imaginary or ideal situation. So in that case, anything less than if the angle of propagation, angle of the source angle is less than the grazing angle is less than critical angle, which in this case is 33, you get a very high reflection coefficient, which means that most of the energy is covered. If you want some math, there's an elegant math associated with that. So this is the Helmholtz equation, which you can solve it, and you can write the pressure as a sum of normal modes. And the quantity wave number is a property of the normal modes, and that can be related to the critical angle. So you can go back and forth from mode and so this is a pictorial representation, which probably is easier to wrap your head around. So this is the sound speed in the bottom column constant. This is sound speed in the bottom. And for a case like this, a simple case like this is called Becker's waveguide. It turns out that these modes, which are the standing wave patterns produced by the interference of the constructive and destructive interference of the acoustic waves, are sinusoids. So basically, this is the first mode, second mode, third mode, and nth mode. And you can see that these are oscillatory in the bottom column, but they decay exponentially in the bottom. And the exponential tail depends on the grazing angle, obviously. As the grazing angle increases or decreases, that will change. And also the quantity which is of interest to the topic that we are discussing is the impedance, which is the product of the density and sound speed. So the extent of this tail, which determines or determines the amount of energy that goes into the bottom and eventually loses, is dependent on the impedance contrast between the water and sea bottom. Now, sea bottom, the climate doesn't have at least too much impact on the sea bottom, so this is going to stay same. But if ocean warms, temperature increases, which in turn will increase the sound speed, so this will change. So the impedance in the water will change, and that will change the impedance contrast between the water and bottom. So that will have an impact on the amount of energy that goes into the bottom. So a scenario here, let's say we have a 10-degree grazing angle hitting the bottom on either side of this Gulf Stream front. So on the one side you have warm Gulf Stream water, on the other side, on the back side, on the coastal side, you have the cold water. So sound speed less on the coastal side, greater on the ocean side. So the difference, so there is a front or a sharp contrast, which ideally you can consider it as vertical, but it's not vertical, it's slanted, which delineates the cold coastal waters and the warm ocean waters. So let's say we have a 10-degree angle, 10-degree grazing angle ray hitting the contrast front. Since the sound speed in the colder side, in the coastal side, is less, the impedance is less there. On the other hand, on the other side, the warm water sound speed is higher, the impedance is higher. So ray on the colder side will penetrate less into the bottom and will suffer less attenuation, less losses than the same angle ray on the warm side. So there is a differential loss, penetration in the bottom, and hence differential loss on either side of the frame. So that's what the point here is. The reason is so anything that goes into the bottom has higher losses compared to the water. So compared to water, and if you compare water and the sea bottom has more loss. So anything which goes deeper into the bottom is going to suffer more loss. So the calculation is here. I won't go too much into the details, but the critical angle on the colder side is higher, 29.6. So the cone of the flashlight is much wider, whereas on the warm side, on the ocean side, is less, 27.3. So it's narrow beam. So this gives a slightly larger angular sector on the colder side, which the sound is not totally lost. It's not a huge difference in the grand scheme of things. So if you compute the percentage difference in the available range of propagation, so the cold side has probably 8% more range or difference in range in the available propagation. It's not a huge amount, but the point we are to notice that so you have so many of these small effects which can either positively interact and magnify things or negatively interact and diminish the effects. So that's what we have to be careful. So the other important thing is that there is a front which is the demarcation between cold and hot warm waters, and so when sound hits the front and tries to go across the front, scattering can occur. Sound can scatter from low angle to higher angle. In a model term, it is called mode coupling. So when there is a sudden change in the properties in range, the modes will shift energy from one mode to another. So that's a complicated, mathematically complicated problem. So that can happen. So a lower order mode, which is typically goes farther and farther in range, can transform or transmit or transfer most of its energy to a higher order mode when it travels across the front. And when higher order mode doesn't go far, so that way the energy can get along faster. So there can be a redistribution of energy among the acoustic modes, which can affect the range of propagation across the front when it tries to go across the front. So that's the bottom line in that case. Another, so I show that slide in the beginning, so indicating that the warming will shift the sound speed back and forth, cold and warm. In addition, sometimes you can have intrusion along the sea bottom. We just now mentioned that sea bottom is the lossiest part of the medium. So what happens here is that so you have a warm water. So when for a layman, if you have to explain sound propagation in the ocean to a layman, you can just say that sound tend to pool or like cold water. So basically, sound eventually will refract around and pool or concentrate in the colder regions of the ocean. So if you believe that, it's going to move away from this bottom warm water and refract upward and try to cool in the colder region. So in a way, this warm bottom layer protects the sound from the bottom. So it basically shields the sound from the bottom, which is a good propagation condition. So sound doesn't interact with the bottom much, less losses, longer range of propagation. So we saw that. So we did an experiment in the eastern United States in 1996, which was my first ocean-going experiment, and this was actual data collected during that time, and we had excellent propagation conditions, and we were wondering what's happening, and when we looked at the CTD data, CTD is temperature data, and reconstructed the sound speed field along the propagation band, we saw this higher, the bright colors, the red and orange are warm or higher sound speed waters, and you can see that the Gulf Stream is on this side, so you can see that the water is hugging the sea bottom, protecting the sound from the bottom protection. So this is happening more often now because of the frequent meandering of the Gulf Stream. Now, a reverse scenario can occur too. Ocean plays in many different ways. So you can have a profile like this, a warm water on top and cold water on the bottom. So if you believe what I just mentioned a few minutes ago, that sound tend to like cold water, then the cold water is going to pool, the sound is going to pool, sound is going to concentrate on this part, which is the bottom, which is going to hug along propagate along the bottom. So you can have a duct of sound propagating along the bottom, downslope into the region. Now, if Gulf Stream comes in and breaks this pattern, so this is the condition which will allow sound to pool in the bottom, but if the water gets heated up, so that duct will go away, that minimum will go away, and the channel or the duct along the bottom will get destroyed. So people have done modeling. So this is they took this sound speed profile. This is a measured sound speed profile. They did some modeling with the source here, and this is a typical parabolic equation modeling, and you can see that the sound eventually finds its way hugging the seafloor into the slope region. So the simple explanation actually can be proved by sophisticated modeling. Other big effect on the climate change is the frequency and the intensity of storms. We have been seeing that in the eastern United States for the last few years. The storms are frequent, the hurricanes are frequent, and they are more violent nowadays. And it can affect the acoustics in two different ways. One is, so when you have big storms, big wind, it will increase the wave activity, the surface becomes rough. And when you have a rough surface, you get scattering, so losses, so sound will get lost due to scattering. So one of the main concern is waves in shallow water. So the basic definition of shallow water is that the water is so shallow that it will have both surface and bottom effects more than a deep water scenario. So the main concern, the first concern is the wave roughness, which introduces scattering losses, and if you allow a simple scattering loss equation, then it depends. So you can see that one of the parameters that drives the scattering loss is the sea surface roughness. So that sigma there is the RMS roughness of the sea surface. So when that increases, the scattering loss increases. The other impact is noise. So the storms are becoming, while I already mentioned that, so this actually happened this year, few months ago, in October. We had an experiment planned somewhere here in the Maryland coast, so that's right there, and we had our instruments deployed there, and we had 2 or 3 storms pass by during a period of 3 weeks, and eventually a big one came in, and we were able to go there and pick up just in time. So actually, when we picked up and we were driving back, the storm basically followed us. That's happening more frequent, so we are losing equipment more and more frequently now to these violent storms. So these storms create a lot of noise, and I mentioned the term soundscape earlier, so that alters the soundscape of the local region also. The difficulty in modeling or anticipating these changes is the difficulty in predicting and forecasting the storms. It's getting better, but it's still there's a lot of mistakes. I think I should speed up now. I mentioned soundscape. The way in which it is defined by biologists is includes both natural and anthropogenic sounds and can be used to give insight into ocean physics, anthropogenic activity in marine ecosystems, and how these vary in time and space. And listening to the underwater soundscapes helps us to understand how ocean's physics and biology of marine communities are responding to a dynamically changing ocean. So one of the indirect impact of the climate change is that the temperature and salinity structure of the ocean is changing. So the biology is redistributing, the marine mammals and fishes are redistributing themselves region-wise, and you are seeing fishes are not supposed to be in some region in some period of the year, and you're seeing them in other places. That will change the soundscape as we know it. It's a problem for modelers, but it can be used as a tool to assess the causes. So basically, you keep on measuring the soundscape, and any change in soundscape can be used as an indicator of change in the biological distribution or storm activity, or which are produced by climate change. So one of the thoughts now circulating among the community is that future studies should perhaps include a soundscape monitoring component, which might be an interesting way to do small and large scale acoustic monitoring. So that's an opportunity for ocean engineers and ocean scientists to understand the impact of climate change. Moving on to Arctic, one of the main concerns is thinning of ice. So that shows the thinning of ice in comparison to the volume of the Grand Canyon. I won't go into the details, but the impact on acoustics is that with younger, thinner, and less ice on the sea surface, underwater sound experiences less transmission loss due to less reflection loss from the Earth's. So that's one direct impact. The other is the stratification that I mentioned earlier, which creates a sound speed minimum in around 100 to 200 meters depth. That is called the scientific term is Beaufort lens, and it appears prominently recently. The data collected in recent experiments have shown that. So it's basically a cool water between two warm water layers, and that will act as a duct again. So sound likes cool water, so basically sound will get trapped in that cool water, and it can propagate longer distance because it doesn't interact with the surface and the bottom, so less losses. So you can get a scenario like this. So so this is not Arctic, by the way. So this is the SOFA channel. But basically, but the principle is the same. So you have a cold water somewhere in the middle of the water column, and if you put a source there, that sound can propagate long distances, continental scale distances if the frequency is right, because there is less losses. So in the Arctic scenario, it is something like this. So there is a warm water on top, a cold water pool there, and then increasing water, warm water on the bottom. And if you have a source there, sound will get trapped there and travel long distances. So these are measurements confirming the existence of Beaufort lens. So this is earlier. So this is 1965 to 1994 average sound speed in the Arctic, right there in the Canada Basin. And this is a recent measurement, the thick line showing the Beaufort lens or the sound speed minimum. And if you model that, if you put a source in that appropriate depth, you can see that sound can travel pretty long distances compared to when the sound speed minimum is not there. Now, if you know where it is, you can use it advantageously, especially for military purposes. But noise also can use that channel to travel long distances, so that will affect the soundscape also. The other interesting aspect is because ice is getting thinner and thinner, new shipping routes are getting started in the Arctic. So this shows the increasing Arctic shipping activity over the years, so 2009 to 2013, and you can see not a linear trend, it's actually a non-linear trend increase in shipping activity. That's going to change the soundscape of Arctic dramatically over the years if these projections are correct. Shipping is one of the major source of noise in the ocean. So just summarizing that part of the talk, I will quickly go through the rest of the talk in a second. So there are some impact on acoustics due to changes in climate. People have started looking into it. Nothing is major except the Arctic stuff, but it needs a little bit more careful research ahead of with some more data. It's going to affect everything that you do in the ocean, one way or the other. So the bottom line is that extensive discussion among the scientific community about how to prioritize research on this topic is required to understand this and to anticipate and tackle the problem. I talked about acidification. That's one of the more controversial, not acoustically but other biological aspects, because it affects corals and animals with shells. It's basically ocean, I already mentioned, acts as a sponge of absorbing carbon dioxide from the atmosphere, and in turn it's turned acidic. So pH decreases, and the numbers projected by IPCC is that by 2050 the pH of seawater is going to drop by 0.3. Not much. And core measurements have done to estimate the reduction in pH in the past years. So they have also found that there was a reduction from 8.2 to 8.1 since 1800. So this is not a new phenomenon; it has been happening, but it's being accelerated because of increase carbon dioxide absorption. It has some direct impact. I won't go into that, but people have talked about that. And the indirect impact is that it reduces the acoustic absorption. So these are the direct impacts. Affects the skeleton and shells, dissolves calcium carbonate, so that will have impact on corals and things like that. But for acoustics, it affects the absorption of the attenuation. So this is the attenuation coefficient. There are three terms. One of them is the borate term, and that term has pH in it. So you can see that in the next slide. This is the full-blown equation, and you have the pH getting into that equation. So when pH changes, the absorption changes. So Ben Reeder and Chin-Chang Hsu looked into this problem, and they modeled the difference in absorption, acoustic noise, actual acoustic noise in deep water, corresponding to two values of attenuation, one corresponding to the 1960s and one corresponding to predictions of year 2050. So two different extreme values. And what they found that was there is a 0.5 dB difference in the acoustic noise, which is not significant, not statistically significant. So their conclusion was that by in itself, the difference in absorption due to pH change is not a big deal. So this is another conclusion. So this is percentage change in the absorption. You can see that it's very low, and the actual alpha values there is very, very, very low. The absorption is very low, and the change of 40% change is not as significant when the value itself is very small. So that's their conclusion. A 40% reduction in the small magnitude of the absorption at frequencies below 1 kilohertz, so this is 1 kilohertz here, is significantly small. But we looked into this in a different context. So we had measurements going on in the Narragansett Bay. It's a small bay, a enclosed water body. So this is the 1, 2, 3, 4 months of data. So the pH is on the top here. 1, 2, 3, 4 years. So 4 years, 4 months, same months. And you can see that the fluctuations are much, much higher than the 0.3% in open ocean. So this is as high as 7.5 to 8.5. So in estuaries and closed bodies, there can be higher fluctuations in pH. So we did some modeling. So this is frequency on the x-axis, absorption on the y-axis. So this is 7.5, the lower end of Narragansett Bay pH, and this is 8.5, the higher end. And you can see that the difference in absorption is as high as 2-3 dB is there. And this is calculate the acoustic absorption at 10 kilometers, at a range of 10 kilometers for two different frequencies, 0.5 hertz and 5 kilohertz and 500 hertz and 5 kilohertz. And you can see that the difference is significant. Fluctuations in acoustic transmission loss 2-3 dB over a range of 10 kilometers at frequencies close to 1 kilohertz. It will have some impact. So because more and more activities are happening in shallow waters and in estuaries and enclosed bodies of water, like pipe driving for construction applications, harbors, jetties, wind turbines. So those kinds of events will propagate farther and will impact marine environment such bodies want. On the other hand, you can treat this as a natural laboratory, and if you continuously measure the propagation loss and the associated pH values, and you can basically understand the impact of pH on propagation at long ranges. So these are long range phenomena. Nothing is going to happen in short range. The last topic, with time, is the impact of offshore wind farms, which is one of the projects that we are actively interested in, is ongoing. So that's why I thought I'll mention that. It's early in the United States, way behind Europe. We just had the first offshore wind farm off Rhode Island, a 30 megawatt turbines wind farm. But more and around 30 projects are being sanctioned and leased out in various stages of preparation. And the estimated potential is of the order of 10 to 20 gigawatt. The problem with US East Coast is that it's the critical pathway for right whale migration. So the North Atlantic right whales are critically endangered species. There are only 100 of them, or hundreds of them, in the whole world. So it's serious stuff. If you harm a right whale, you can be in serious trouble. So the developers have to spend lots and lots of money to do modeling and studies to convince the licensing authorities that they will take all precautionary measures not to harm North Atlantic right whales. So all of the studies that we have been doing is geared towards the right whale frequencies and their aspects. So there's a big project which are going on. I won't go into the details. It's funded by Bureau of Energy Management, which is one of the licensing authority for granting leases to offshore developers. So during the first wind farm construction, we did measurements during pile driving. We measured both the acoustic noise and particle velocity. So this was a jacket type of structure, the typical offshore petroleum rig type structure. Each leg of the jacket was raked inclined at 13 degrees, which has some significance in the propagation of acoustic waves. In the next talk after lunch, I have some simulations and things like that. So I will talk more about that. So we also measured the acoustic radiation or noise radiation during operation of the wind farm multiple times, multiple seasons and things like that. So it's pretty comprehensive study which is still ongoing in the next wind farm in the next couple of years. So we had a bottom-mounted hydrophone, geophone array, vertical line arrays, towed arrays, dipping sensors, whole suite of sensors at different ranges. So this is one of the significant results. So this is the sound pressure level, dBr 1 micropascal peak sound pressure levels as a function of range away from the wind turbine. And the closest that we could make measurement was half a kilometer, so that's this point right there. So the numbers there is significant, 190, 185 dB, 1 micropascal peak. So this is the result from towed array. So you can see that so these are 2 different days, 2 different pile legs. Later on, we wondered why they are so different, and then we found out that because of the inclination of the legs, there is a azimuthal dependence to the sound propagation, something like a beam pattern. So depending upon which direction the pile is inclined, you could get a higher SPL or a lower sound pressure level at the same point. But the bottom line is that during pile driving, during construction, these wind farms produce a whole heck of sound. On the other hand, during operation, it's not much. So this is the only signal that he could detect, which we think is from the wind farm. This is like a constant frequency around 72 hertz. So this is our fin whale vocalization, which are much louder. So these fin whales are vocalizing at 50 to 100 kilometers a day at 20 hertz. So it's low frequency, so they travel far. The turbine noise is roughly 90 dB. So earlier we talked about 185, 190. This is 90 dB, much less. So that's our conclusion. Whale, ships, and wind louder than a single wind farm. The other important consideration for the study was to understand the impact of particle velocity on fish behavior and fish mortality. Apparently, I'm not a biologist, but I learned over this project that fish sense the sound through vibrations or particle motion, not by sound as we hear it. So they have something like an accelerometer in their ear, and that's how they sense the vibrations. So people have measured the audiograms. If you go to an audiologist, they measure the audiograms. So people have put fishes in cages and also through neurological methods measured the minimum particle velocity levels that they can hear. So they produce curves like this. So our task was to measure the particle velocity and see whether the fish can hear it and how severe it will be impacted. And this is our primary result. So during construction, the fish will definitely hear it, and so this is the minimum they can hear, and the levels are much higher. While during operation, there's nothing much. On the sensor on the sea bottom, that's 72 hertz. Probably they will hear it. So there is a difference between measurements in sea bottom and this is measurement made in water. So there's a difference. That's because the wave types are different. I will talk about that more in the afternoon talk. So if the fish is lying on the bottom, then it's likely that they will have some impact from the operation of wind turbine. SPL wise, the pressure wise, sound pressure wise, the construction levels are much higher, the operation levels are much lower. So the fish will not be affected much during operation. So that was our conclusion here. But, so this is just repeating the conclusions, but the one thing which you have to be careful is that, so we made measurements on one turbine, but generally these offshore wind turbines consist of hundreds of turbines. While construction, they are mandated to construct one leg at a time, so so the construction modeling and measurement will not change. But when they are all operating, the 100 different turbines are operating simultaneously, and they are producing sound in all directions, and they will constructively and destructively interfere, producing some sort of a probably an azimuthal dependent cumulative noise radiation, which we haven't studied, which nobody that I know of have studied, and that probably will have, I'm speculating here, will have some impact on marine mammals and fish. So that's what I have, and the final thought I kept it simple. Having gone through all this litany of concerns, I think the effect of climate change on ocean acoustics have multiple aspects of impact. Some of them are big, some of them are small. The Arctic is big, shallow water probably is not that big, but combine this with acidification and the increasing shipping activity, the new types of noise sources, how they interact with each other, and how they produce significant changes in soundscape. Those are things which needs further investigation, and smart engineering solutions like soundscape monitoring probably could provide some insight into the long-term monitoring of the impact of climate change. Okay, that's my last slide. And I thank you all for patient listening. And I'll be happy to take any questions.
Will aid the data transfer from the underwater instrumentation systems?
We're talking about communication.
Yes.
There will be impact on communication. I have studied that. People have looked into that, and the propagation conditions will change, and that will have impact on the way sound travels and the data rates and those kinds of things. It depends on where you are also. So if you are in Arctic, you have more impact. So it's regional specific. So the effects will be specific to a region, driven by oceanographic conditions, oceanographic changes. So nothing is going to be drastic, but so we have to keep investigating that.
Melting of the polar ice caps and sea level rise is adding more water into the ocean. Whether it is counteracting the acidification, is it not?
That probably is true, but what I have here is all measurement, so it's all measurement based. As we say, data never lie. So there is some changes in the acidification, but as I said in the talk, the acidification in the open ocean is probably not a big deal. I mean, often some of the climate change advocates when I say that, but the analysis by Ben Reeder and Ching-San Chu shows that the noise level increases or changes by 0.5 dBs statistically in sea. But it's again regional specific, location specific. If you go into a constrained environment, then the changes can be much higher. So the Arctic melting probably will add more fresh water in there. Probably. I'm not confident about that aspect. looks like everybody is tired and ready for lunch.
Thank you, sir, for providing us with the insights into the effects of climatic change on underwater acoustics. As a token of gratitude, we would like to present a memento for the speaker. May I request Ms. Shobha Verma for presenting the memento.
Thank you very much.
Presenters of research session on signal processing are requested to hand over their PPT to the presentation desk.